Good afternoon to everyone gathered here. On behalf of the Physics Society, I would like to welcome all of you to the 29th edition of the annual R.K. Popli Memorial Lecture Series. This event is organized in the fond memory of the late Dr. R.K. Popli, who was a beloved teacher, a fine physicist, and a kind human being, who taught here at St. Stephen's College from 1971 to 1994. Our speaker for this year's lecture series is Professor Gautam I. Menon, from the Department of Physics and Trivedi School of Biosciences, Ashoka University. Professor Menon is the director of its Center for Climate Change and Sustainability and was recently appointed as the Commissioner on the Lancet Commission on Epidemiological Modeling. The topic for this year's lecture series is the evolution of a physicist. Over the course of the next 3 days, Professor Menon will stimulate young minds on 3 important topics related to physics and the ongoing research in it. Prior to joining Ashoka, he spent more than 2 decades at the Institute of Mathematical Sciences in Chennai, where he was the founding dean of the Computational Biology Group. He was also awarded the Swarna Jayanti Fellowship in 2005 and the DAE SRC Outstanding Researcher Fellowship in 2010. He was named an outstanding referee by the American Physical Society, an honor conferred to less than 1% of its reviewers worldwide. He was a member of the expert group that drafted the Science, Technology and Innovation Policy of India in 2022. In 2022, Apolitical named him its list of 100 most influential academics in government worldwide. I'm also delighted to share with all of you that Sir is an alumnus of our college. Sir, we are extremely privileged to have you in this studio. I would now like to request our head of the department, Dr. Sangeeta Sachdeva, to share a few words and to present a bouquet of flowers to our esteemed speaker and inaugurate you.
Dear senior members, junior members, our speaker, Professor Menon, and accompanied by his wife, Ma'am Ananya, I welcome you all for this prestigious 29th annual Popli Memorial Series. It's a 3-day lecture, very, very important for our growth and development, in a very, very fond memory of our beloved teacher, whom I've never met, I've never seen him, never met him, but what I've heard about him is about his passion for the subject which we want to inculcate in our students. So I inaugurate this prestigious Popli series.
Without further ado, I would like to invite our speaker, Dr. Menon, to take the stage and begin his lecture. I would also request him to share about his association and the list of topics.
Thank you so much for that very kind introduction. I must be one of the few people in this audience who have actually taught by Dr. Popli. It's roughly now about 4 decades since I entered this room for the first time, so you can figure out how old I am from that calculation. Dr. Popli was a smallish man, he wasn't a tall man, he was small. He was some Tintin character in a sense, you know. He had glasses, he was very serious looking, and he was an exceptional teacher. I mean, it's again something that you have seen his photograph, you know what he looks like, but to actually have him in a class teaching you was actually a very special feeling. And there were a bunch of really good teachers that we had at that time, but among them, Professor Gautam was another one among them. But he was very, very special in his ability to convey to a class ideas behind physics, especially around mathematical. So, I think the best thing that I could do is to tell you something that he taught me that actually has stayed with me for a long time. And so the scenario is this, that this was my first year in college. I think it was a break between, probably in October or something, short break that we had. And he said, when you go back home, I want you to think about a particular problem. And the problem was a problem of calculating a particular integral. I just draw that for you. That integral was this integral. So some of you who've seen this, you know what the function will look like. This is a function that looks like this. It's symmetric for x continuous. And one might think of how to calculate it. Will you integrate by parts? What will you do? To try many tricks out on this. But actually none of them really work very well. What works is a really interesting idea. Okay, so he said, look, you go back home, think about it, let's see what you can do, etc. And we came back and none of us had the answer. So then in a few minutes on the board, he showed us how to do this integral. And it's a great example of how to think about difficult problems. And the secret here is not to do this integral, but do an integral that looks much more difficult. That is to do an integral, which is the integral of I squared. So that seems much harder. Already I is hard. I squared must be much harder. But let's just see how one might do that. So the idea is that to break it up as minus infinity to infinity, x is from minus x squared. And then exploiting the fact that I could have called it x or y, doesn't matter, it's a dummy variable. This is dy e to the power minus x squared. And this is the same x squared. Okay? So this looks weird. Instead of calculating I, we're now calculating I squared. Why would anybody want to do that? So the trick is now sort of rewrite it in a slightly different way. And write this as minus infinity to infinity dx dy e to the power minus x squared plus y squared. We're just combining these two, writing these two integrals that you wrote separately as one integral. Now you do the following. You write x equal to r sin theta, y equal to r cosine theta. And then this term here becomes e to the power minus r. This integral dx dy becomes r dr d. R integral goes from 0 to infinity. The theta integral goes from 0 to infinity. Okay. We still have dr and d theta, so dx and dy. But somehow everything here really depends only upon r. And the theta is almost a trivial thing to do. That integral you can do, that's a factor of pi that you get. And then there's an integral minus 0 to infinity dr r e to the power minus r squared. Okay. Now the simple trick, multiply and divide by 2. And remember that the derivative of r squared is 2r. We factor the sign, do this particular integral. So to finally get it, I squared is 5. Okay, because the factors of 2 cancel. The simple only contribute only at the lower limit, which is 1. And miraculously, it's a simple integral which you can do by parts. Anyone can do an integral by parts. You get this answer. So therefore, I is very hard. Okay? For those who haven't seen this, it sort of looks like magic. Those who've seen it, many of your expertise in the audience will know this very well. But it just illustrates a point that I think is a beautiful point, that when you're a young student coming and seeing something like this, you really understand the beauty of a different type of argument. It's not a standard argument. You make the problem more difficult, and then you do interesting symmetries behind that problem, the right choice of coordinate, the right choice of transformation. You do something that's almost magical. And the fact that this integral has anything to do with pi is very surprising. Pi is 3.1 is a transcendental number. And the fact that you can derive this result from that is itself quite interesting. This is what Dr. Popli taught me 4 decades ago. This is something that I've never really forgotten since then. And again, this is something that you've seen now, those who have not seen it earlier should remember this. But you should remember it not just because it's a clever way of doing the integral, you can do many other integrals like this. The Gaussian integral, which is what this is fundamental to a whole lot of physics, including quantum field theory of many types. So it's very good to understand how you get this and what effects may come with this. It's also good to remember that there are elegant and beautiful ways of thinking about something. That's the point. That's not the topic of this lecture. This is actually lecture spread out over 3 days on different things that I have worked on or been interested in. I normally would not have given this lecture because it's too much about myself, but I thought it might be interesting just to show how physics training is useful for others. Many of you are interested in other parts of physics. Some of you will do particle physics, some of you will not do physics at all, which is perfectly fine. Those of you who will do physics may do types of experimental physics, astrophysics, particle physics, mathematical physics, etc. And we make these choices because we find them interesting and we find something that really appeals to us in that particular subject. So there have been many things that have appealed to me in my life. And I just want to take you through 3 of them, the lessons that I have learned from them, and to try and explain to you why these problems are interesting in the first place and why other people, apart from myself, now consider them to be, in a sense, important, the topic of study for the future, which I hope in my future of biophysics will stimulate you to think about things that are different from what you have learned under normal circumstances. And on the 3rd day, we will talk about infectious diseases, which is very different from what you would never encounter that in a physics classroom. But nevertheless, ideas from physics are important in topics such as that. So let me start by talking about superconductivity, and that's the topic of my first lecture. And there, let me just remind you of what the standard experiment might be that measures the resistance of an object. You take a piece of material here, you have a battery here, you pass it to the voltmeter here, and you measure the voltage drop across the material like this. What relates the voltage and the current for the sample is relation to V equal to IR. If I make a mistake on the board, it's very good to point it out. Stuff I'm teaching without notes, without really from memory. So you must let me know if I make a mistake, because then we can correct it or you can help me correct it together. Alright. So this is the relationship between the current that flows through here, the I, the voltage that is applied across this, and the resistance. And we know that the resistance itself is proportional to the area, what is the length of the sample, what is the area of the sample, and the factor that comes in is the resistance. Okay. By writing the NNA out separately, we got rid of the physical dimensions of the sample and concentrated on the one quantity that is actually meaningful, that represents the property of the material that we're trying to look at, and not the shape in which you cut out or broke it out or someone gave it a crystal. The measurement here is the measurement of the resistivity as a function of temperature. And I wanted to now go back to 1911, and before that, more than a century and a decade or so. When people began to do these experiments, right, these experiments have a long history before that, but it was the first time people were able to push these experiments to lower and lower and lower temperature. So the person who was doing these experiments was a gentleman called Cameling Ons, and he was doing them at Leiden in the Netherlands in 1912. So Leiden was famous because at that point it was called the coldest place in the world. And it was called the closest place in the world because this gentleman was an expert in low temperature. He was a person who was liquefied helium and then used liquid helium to investigate the properties of a whole lot of materials at very, very, very low temperature. By very low temperature, I mean around 4 Kelvin or less. Okay. And so that's minus 269 degrees centigrade, whatever it is. Yes. Okay. So what Ons expected, based on what had been learned earlier, is that the resistivity has the following behavior. Typically, it could either do this, or it could do something like this. This is all understood from measurements that were done at 200 centigrade, 250 centigrade, etc. We found these categories of materials, and this is what we call an insulator. And this is what we call a metal. So now the question was, if I cool everything down to low enough temperature, will they behave like this or like this? what happens? Can we say? There was some idea that they would all behave like this in some way, but no one could actually test it until they actually had access to their data. So, what Mr. Anand found on that fateful day in 1907, I think he was looking at mercury, and the spirit of mercury was not too bad. He found it was sort of going down like this. Until some point, we're actually seeing to be immeasurably small. That is to say, nothing, no measuring device that he had to measure the resistivity of this would give a number other than zero, basically stuck resolution. This was very hard to comprehend because this was not included either in the sort of smooth behavior like this or smooth behavior going down like that. It was something completely different. It seemed as though there was some sharp type of different type of behavior that happened here. We call this the constant temperature or the PC, at which the resistance vanished. Equivalently, because the resistivity and the conductivity are inversely related to each other, if the conductivity became infinite. So the word he applied to was that this became a superconductor. So now the question is, what is a superconductor? Why does the material do this? And at that point, it was understood that the carrier, if you took a piece of the metal like this, you had charge carriers inside that, and mostly, if not all the time, these charge carriers were electrons inside. It was electrons that were moving around and carrying the current. The mental picture that you should have is, you have an electron here, so you have one electron here. This electron is coming in, scattering off some impurity here, going off here, going off here, going off here. So rather than move in one straight line, the motion of an electron in the field that you apply is this sort of jagged, rough. It's basically moving more or less in the direction it lies field, but it's not accelerating in that direction. If I take a charged particle and put it in an electric field, it should normally accelerate, but it's not doing that with the relationship. I get a fixed current for a fixed electric field that I actually apply. Alright? So, in order to understand this particular relationship, he went back to Ohm's law. Alright? And Ohm's law just says that this is the relationship between electric field that is applied and the current that is passed through the current. The current is the electric current density. I divided by A. So if you put in this, if you remember the fact that the voltage drop times the distance to the electric field, you wind up with an equation where J is sigma times E, and sigma is the conductivity. Okay. It's this object that will become infinite for some reason. You can take this idea of something going, jumping off here, scattering here, scattering here, scattering here. What does it imply for the conductivity sigma? What is that? The idea is very simple, and we won't do that calculation here. But if it spends roughly a time tau in between colliding, and in each collision it gets completely randomized, it hits here and goes back here, goes back here, goes back. If the mean time between these collisions is tau, then sigma is the density of electrons, the square of the electronic charge, the tau that I talked about here, and the mass of the electron. This is an important fundamental relation that is derived from a picture like this, but that is writing it down quick. Okay? If you haven't seen this, it doesn't matter. You'll see it sooner or later at some point. But just look at what it contains. It says the conductivity depends upon the number of things that there are to carry the current, the charge density. It depends upon the square of the charge that must enter somewhere. It depends upon the time between collisions. So the longer that time takes, the larger the conductivity. Instead of the square, you contribute to larger. And the mass, the heavier the object is, the lower the contribution to conductivity, because it moves somewhat with an inertia. It moves somewhat more slowly, and the action makes sense. So the only way out of this way for sigma to become infinite is you can't change the mass, you can't change the number of carriers, you can't change the electric charge. They put tau in front of it to become infinite. So the only way for sigma to go off to infinity is for tau to go off to infinity. But that doesn't make sense. But this means that the electron is not scattering off anything, it's just getting more and more and more and more and more and more energy. It's just going fast and fast and accelerating. and then you can't do inside, so you put them in a standard electric field. That doesn't make sense again. Okay, something just keep accelerating on to infinity. It's going to cost you an infinite amount of energy to actually do that. So that cannot be the answer. And then for many, many years, people were simply stuck with this idea that, look, here's a nice formula, we can derive this formula. You ask from here how to tell you that sigma can become infinite. It says the only way for that to happen is for the time between positions to become very large. That doesn't make sense because it is not colliding with anything, it's just accelerating, it's just warming up, becomes everything. Moving faster and faster and faster. At some point, it basically the speed of light, of course, we know cannot happen. So this whole idea must break down at some point. And we must rethink what happens when something goes different. So this was 1911. In 1913, Mr. Ram, I think it was 1913, gets his Nobel Prize. Maybe the most space in the world is actually, discovering the helium and superconductivity, etc. I think the field is sort of, no one sort of goes near it. But many interesting things are happening. Quantum mechanics is being good at it, wave mechanics is coming along, all of this. Einstein produces the general theory of relativity in 1916. Many changes are happening in the field as we know it. And someone says, okay, we don't know about this matter, we just put it aside. We won't think about it in the time. Until 1933. When a gentleman called Menon and another gentleman called Popli figured out something interesting. And again, these were experimenters. So their experiment was take a piece of superconductor here, superconducting for field less than DC, and look at its behavior inside the light magnetic field. So they took their sample, put it in the magnetic field, and then cooled it down. Rather than just measuring the resistivity, which is this measurement here, what they measured was what is the magnetization of this particular thing. Okay? Very straightforward. What they found was that I got minus 4 pi times the magnetization here, and I got magnetic field here. They found something that looks like this. This is some equal value of the magnetic field. Okay? This is at low temperature, just increasing the magnetic field. I've chosen this minus 4 pi m for a particular reason, which is not a good reason. Because the relationship between B, H and M is B equal to H plus 4 pi m in CGS units. So I'm only going to do CGS units here. And I apologize for this. We translate all of this into MPS units, so there won't be a factor of 4 pi here. But some of the field is written in CGS, some of it is in MPS. And it's a challenge to you or a task for you to convert everything back to MPS at some data point if you want. So what is this saying? This is saying the relationship with is H equal to 4 pi m. Then this term must match. I think I have got the sign now. Okay. Then I take H to the side, and that's still not right. Yeah, B equal to 0, take H to the side is 4 pi B. So this means that the B is 0, which means that inside the magnetic field, inside the sample of the superconductor, there is no magnetic field. Okay? Now this is weird, because for temperatures larger than DC, the field enters very high. And the magnetization is effectively 0. But the moment you go below the GC, the moment the sample becomes superconducting, somehow it pushes the magnetic field out. How does it do that? Well, you have a hint there, somewhat the magnetization is doing. The hint there is this. You have your sample here, you have your external magnetic field here. The sample develops currents inside it that precisely cancel the external magnetic field. These currents around the sample give you a magnetization. The magnetization is directed oppositely to the magnetic field. So if you sit inside, deep inside here, you don't see a magnetic field at all. This is called the Meissner effect. So now we are at 1933. My friend doesn't get a Nobel Prize for this discovery, but it changes everything. So now people say that, look, maybe it's not the fact that the conductivity is infinite. Maybe it's the fact that's important, that the magnetic field is not allowed inside. Some of superconductors are these ring objects, which create a current around themselves, a circulating current that's a superconductor themselves, that precisely cancels the external field into zero inside. That's again a great step. After that, a sort of explosion of activity began. And the people responsible for that are a bunch of people. And the most important names among them are the brothers London, Landau, Wilford, a whole bunch of other people who began thinking about this. The London brothers, in a sense, were the most important British contribution. What they said, in essence, I'm not cutting across a whole lot of technical detail because I don't know, is that this relationship must now be modified. Rather than the current being proportional to electric field, the current proportional to something called the vector potential. The vector potential is obtained as B is del cross A. This is the relationship. This is the new equation that replaces A with sigma U. And this is the equation that they argue is the right one for a superconductor. Again, it's possible to explain all this in great detail, but I won't do that because my time is limited. Let me just tell you one consequence of this particular observation. One consequence of this is, basically you can figure out that very carefully. Just take the del cross on both sides. Del cross A is the magnetic field. Del cross J you can figure out from Maxwell's equation. You relate to del cross B. Because del dot B equal to 0, that is minus del square B. Finally, you have del square B equal to 1 over lambda square times. That's the sort of final insight that you can get. It's actually a somewhat different quantity, lambda, because there are mu's and so on, etc. Not from the Maxwell's equation, that I will do that. Let's put that at that. What this means is, the solution for this that makes sense is that B is D0 e power minus R divided by lambda. That is to say, suppose I have a superconducting layer and a vacuum layer in which I have a magnetic field. That field will decay exponentially and then inside the sample. And the decay across which that happens is this lambda, which is called the penetration depth. Alright? Are you with me so far? Am I confusing you? Are there glimmers of understanding? But this is a solution to what was found by Menon. If you change the relationship between the current and the magnetic field, del cross J is E, then you solve the problem and you find that field cannot enter the superconductor. It will always be screened out by currents that are flowing at the surface. It's those currents that cancel, allow you to cancel the field. The next major step was to say that we now have to have a revolution in the way we think about these things. We cannot think about a classical picture of things scattering all inside. We have to think now in terms of quantum mechanics. And that's a real change in ideas that we reach this point. What does that idea mean? That idea means that instead of thinking about individual electrons, we think of these electrons as, in some sense, belonging to the same state, the same quantum state. If you remember, we have the idea of a quantum state from quantum mechanics. And we know that we're allowed to fill electrons into quantum states, but you have to obey the Popli principle. What that means is, suppose I say I have quantum states here, 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 here. I'm allowed to put electrons here, electrons here, electrons here. But I cannot put more than 2 electrons up and down spin in the same state. It looks like this is fundamentally contradictory to the idea that in order to solve the problem of superconductivity, you must have many electrons in the same state. So this held up further progress in the field for another 20 years until people began to figure out this particular reason for why it might be happening. People who finally solved this problem were a set of three thread theorists, Barney, Cooper, and Schrieffer. All very famous names. Do you know why this name is famous?
He got 2 Nobel Prizes for physics.
That's right. What is the other one for?
Transistors.
For the
Transistors.
So he's the only person to get 2 Nobel Prizes in physics. Well, I'm sure he got one for physics and for chemistry. That's right. So what Barney and Cooper did was to say that, look, if you find a way of pairing electrons in some way, this paired set of electrons doesn't behave like single electrons anymore, they behave like a boson. One simple way of thinking about it, if you got them to come close enough together to form something like a molecule, this is the spin 0 object, this is spin 0 or spin 1 object. And this could, in principle, circumvent the requirement of Fermi set of sets and allow you to condense a lot of these things onto the same. There are some subtleties here which I won't tell you about. The idea of pairing is actually correct. But it's a subtle form of pairing, where you have to pair not just things that are physically close together in physical space, but electrons in states, in a mental state, that are going opposite to each other. You don't worry about that detail because it's not relevant here. All of this, of the idea behind pairing electrons, the fact that this would solve superconductivity, really is part of this very beautiful and powerful paper by Barney Cooper, who almost immediately got them the Nobel Prize within the next 3 to 4 years for that. It was a very fundamental and beautiful idea. And because the number of things that they could actually calculate, they showed that the Meissner effect was a consequence of this. Many different types of experiments could be explained by the idea that they got to. And pairing was fundamental to this particular idea. Pairing was called a gap. So I want to this is just background. I wanted to tell you a little bit about my own interest. And to do that, I have to tell you a little bit more about the superconductor itself. So far what we did, if you remember the Meissner experiment, Meissner said that if I take the temperature, plot the magnetic field here in this direction, then below this temperature, below field dependent temperature, which is COP, this was a Meissner phase. And in the Meissner phase, the field would not enter, go around like this. It wouldn't enter the sun. So this was understood, this was plotted, there were many experiments that did this. But there were many experiments that did not show this type of behavior. What they showed was that instead of having something where you have 4, 5, and numbers as a function of space going like this, you had something that instead went like this. You're measuring a magnetization. But rather than sort of increasing with the field and suddenly going to zero. So it's increasing a bit and then coming down and coming down and coming down and coming down. But really going to zero at a much larger field than you might have imagined. If you change the temperature, you have something went up like this and then went up like this. It could be different. So how would one accommodate that? But the idea there is that you have a different type of what's called a phase diagram. Again, field here, temperature here. At low temperatures, you have the same idea of Meissner, but at fields that are somewhat larger, you have something new here, which is called the mixed phase. And of course, what's on this side is the normal phase, normal, non-superconducting phase. The mixed phase allows some field to enter, but not all the field to enter. So you go up from here, no field enters at all, some field enters, more and more enters, more and more enters, and you find here the whole field enters. So in between. That's why it's called mixed, because it's mixed between the completely normal and the light phase. So what's happening here? That's interesting here. What happens there is somewhat unusual. The field is entering, but unlike the case where the field entered, where you had a magnetization that prevented it from going inside, the field enters in a somewhat subtle way. It enters in the following way. It enters in the form of lines. So let's look at the sample again. Here is our sample. Here is the external field that I'm applying here. The magnetic field entering the sample, like a sort of narrow cylinder here, a whole bunch of narrow cylinders here. If I look inside the narrow cylinder, the field is maximum here and then goes down there to the middle. As I look around the cylinder, I see lines of current that are circulating around. Far away from this, so this region is normal in a sense. Far away from this, you have superconducting material here. So it's a very unusual, it's like a strange lattice of lines of magnetic flux that are separated by regions that are superconducting, that are protected by circulating currents that move around it. And they form a triangular lattice. That is, if I looked at it from the top, I looked at the arrangement here, and the arrangement would look like a bunch of triangles together. As I increase the magnetic field, the triangles come closer and closer together until the point where everything overlaps so much that the sample is mainly normal. It's not superconducting. That's the idea of the concept. The person who discovered this was a person called Abrikosov. And this Abrikosov was a student of, I forgot his name, of Landau. And the story goes that Abrikosov found this when he was doing his PhD and took it to his PhD advisor and said, "Hey, I have this wonderful new result at finding this PhD." And his advisor refused to believe him and said, "You must be wrong. Go back and go and check again." It's to Abrikosov's credit that he pursued it despite the fact that the very, very, very famous Nobel Prize-winning advisor told him that, "Look, you must be wrong." And he wound up getting a Nobel Prize much later, 30, 40 years later after he discovered it. But it's an amazing idea. He discovered it theoretically, not experimentally. He found out that he derived external behavior from equations that experiments with superconductors. He was able to show that. He was able to show that they formed a triangular lattice. Actually, he made a mistake there. He first showed that they formed a square lattice. It had to be corrected a few months later by someone who said, "No, the triangular lattice has a lower angle, square lattice," and then he made it better. But everything else was there in that case. So now you have this funny lattice. And it's like nothing that you've seen before. Because it's not a lattice made up of individual atoms that are placed together regularly. You see, when you do your solid-state physics, you think about chromium, structural fluid storage, etc. It's an atom placed in a field. These are not atoms, these are many atoms together, many electrons together. If you look at the size of this, it could be something like 100 angstroms or more within this region. So it's a strange quantum mechanical collective type behavior that gives you a lattice. All of this became very much more interesting. After Abrikosov discovered this, there was some amount of work following up on that. But everything changed in 1986. In 1986, there was a revolution that happened, and that is the revolution of high temperature superconductivity. Or Mr. Kamerlingh was struggling to get this thing at 4.2 degrees Kelvin, the temperature that we utilized in here. But suddenly it seemed possible for things to become superconducting, not at 4, not at 14, not at 24, 34, 54, 64, but at something like 80 or 90 Kelvin, much larger. Menon and Muller first made a big step of synthesizing a bunch of compounds that were a significant improvement on earlier compounds. And then the field just ran away with that. And people now, I think the world record is probably 120 Kelvin. Still not room temperature. You will still read about the paper occasionally, claims of a new room temperature superconductor, but we haven't got there yet. Very far away. So when that happened, the question was, what happens to these lines at high enough temperature? These lines are perfectly nice and form perfect lattices, provided that you're at 4 degrees Kelvin. But if you're at 80 degrees Kelvin, what happens to these lines? And there's only one important thing that happens to any crystal to increase the temperature, and it's at the crystal melts. So then the question was, if you had a line lattice, a triangular lattice of line, could it melt? How would you be able to tell? What are the sort of experiments at night? These experiments are hard because they're not, as I said, they're groups of very, very large aggregates of numbers of electrons and so on. So the changes in entropy, any changes are actually very small and subtle and hard to measure. So one must figure out types of experiments to understand this and think about what would happen to that. That's one set of questions that I looked at. The interesting, I want to tell you a little bit about one experiment that was what we focused on. And that is something called a nuance spin rotation experiment. This is a nice experiment because it combines many different fields in a sense. The mu here is a subatomic particle called muon. A muon comes from the same family as the electron does. The electrons, muon, and the tau together. This is an unstable particle. It decays very fast. So the decay is muon, become electron, become positron, and actually neutrino, and then there is something like this. Maybe it's a photon. But this lives all together for about 2 microseconds. That's all it is. But most importantly for our purposes, it has a magnetic moment, and when it decays, the positron that comes out decays asymmetrically with respect to the direction of the magnetic moment. That is, more are emitted in this direction than in this direction. That might look like a very minor observation. It's really a consequence of what is called weak interaction. That allows us to have. How is this useful at all? It's useful in the following way. I take muons, I polarize them, I point them all in the same direction, and I push them into the sample. Once in the sample, I can do that very fast, that takes very little time at all. Once in the sample, each muon magnetic moment senses the magnetic field around it. When it senses the field, it begins to precess around that, just pointing in this particular direction. And the rate of precession depends upon the strength of the magnetic field. When it decays, it's decaying asymmetrically. So I put a detector here and a detector here, I can detect that asymmetry. From measurements of this asymmetry, I can figure out what is the field that muon will see at that point. If I do this many, many times, I can actually map out the internal field in this direction. The map of the internal field is really the map of the distribution, because the field is largest here and smallest in between these lines. So it's a clever experiment because you do need a lot of participants to do this experiment. But it's a use of particle physics experiment in mathematical physics or solid state context that provides you very beautiful information that you could not have ever got otherwise. So this is a set of experiments that we looked at to try and understand how does melting happen, how are these lines arranged, and then the glassy faces of these lines, all these questions that we actually address. There's one set of questions that I looked at is my PhD. The other set of questions has to do with the phase diagram itself. As I said, we have these phases here. Here is the mixed phase, which should have been a perfect triangular lattice, but can melt. Inside here, we have a melting line that looks like this. So this is magnetic field here. The slope of this melting line is a bit unusual and has very specific and interesting consequences. And I can point that out to you by reminding you of what the PT phase diagram looks like for an ordinary liquid as well as for ice. For ordinary liquid, it points in this direction. So this is gas, this is liquid, this is solid. But for ice, it points slightly to the opposite source in that direction. This is responsible for life on Earth, by the way. So if it had not, this tells you how the tops of rivers can freeze and leaving water inside for people to survive. But this also has an interesting consequence. This is the fact of why ice floats on water. The fact that this floats is the opposite side. But that's something like what happens here. That suggests that the solid here is less dense than the liquid because it behaves like ice in that sense. That's another thing that we pointed out as well. These are unusual types of behavior. There's an interesting corollary to this, and with that maybe I should finish up. And that is that this phenomenon of this type of stroke has been used to explain one thing, which is how ice skaters skate. If you remember the normal explanation for this, it's that when you apply pressure on ice, you're basically sort of going up a little bit here. Your melting point of ice is shifting downwards, and therefore you form a little skin of water between your ice skate and the ice surface. It's this skin of water that potentially helps you ski fast, move much faster. If you see ice skaters on TV or something, you can see they move extremely fast, very, very fast sport. And ice hockey is probably the fastest sport there is because of the skin. This explanation is wrong, because it turns out that if you put the numbers in, it's not sufficient to really melt ice at the temperature that is what normally the ice. What happens instead is, if you take ice at low temperature, there's a layer of melted ice, layer of water above, which is always there. It's extremely equilibrium is always there. And the fact that it's always there is what enables the skater to actually skate, because it exists as part of that. The same thing, interestingly, holds in this case. That even though you can be solid inside, as you move towards the surface, you have a little layer of liquid lying on top. That's again an interesting thing to get understand by combining those things from understanding of the regular phase diagram there and what we change it in this more important context. There's more that I could tell you about these stories of what can be done with the superconductor. But I wanted to make a couple of final points just to sort of get into your head of what this is. Superconductivity is an amazing quantum mechanical phenomenon. It happens because 10 to the 23 electrons inside the sample suddenly decide that they want to be in the same single quantum. This is forbidden by standard laws of quantum mechanics. But the way around those laws is to allow these electrons to pair. If you allow these electrons to pair, effectively they behave like bosons, and bosons can have any number than in a quantum state. So, superconductivity is most like the phenomenon of many electrons together in a paired state, coming into a single common state, condensing into a single common state, and then after behaving like one object, one large coherent quantum mechanical object, which then everything has to happen at the same time. You can't have each electron here doing individual things, because they all belong to the same single wave function. So that's where quantum mechanics actually enters in deep level. That ideas from here can then be transferred on other subject systems. The second message is that superconductivity and magnetism are very inextricably tied up together. The first example of this was the Meissner effect, where we understood that the field, if you're not at high field, the field is tend to go out of the sample, and it does this by achieving this remarkable cancellation by having current that circulate and give you a net magnetic moment that precisely cancels out the external field that is applied. That's the second important point that you have to make. That you cannot understand the phenomenon of superconductivity without understanding its relationship to magnetism. So the single quantum state, the importance of quantum mechanics, and the importance of magnetism. The last point is that even within that universe of superconductors and magnetism, there's scope for a whole lot of variety. The simplest thing is, of course, the field that's going out. But the next most complicated version is completely unanticipated version. Either the field enters in the form of lines of magnetic flux. We didn't talk about magnetic flux so much, but it turns out that each of these have a quantized flux of Hc divided by E star in this particular case. Again, that's unusual. Very specifically quantum mechanical. It contains the universal constants H, C, and E. And you cannot take H to 0. That's again an indication that it's very quantum mechanical. You could not have guessed this. Someone had to sit this step. Someone had to sit and calculate this and go to his advisor to have his advisor tell him that he got wrong. Nevertheless, come back, write his paper, and of course get it over by 30 years later. It's remarkable and assumption. So a bunch of lessons in here. Don't always believe people when they tell you that you're wrong. Even when your advisor is planned out, you should, if your understanding of physics is deep enough that Professor is, then you should be able to hold to your convictions. Very specifically. And the other is that reducing quantum mechanics is very apparent here. There are many places, there's quantum computing, there's quantum information, many other areas. But here's this old traditional field of conducting, now more than 120 years old, where all these questions really came up for the first time. It's still struggling with some of these interpretations right now. But the experiments that I told you about, the non-demonstration experiment that combines particle physics ideas and weak interaction with a detailed measurement of what's going on inside the conductor. These point an interesting fertilization between fields. People from, even if you're a particle physics experimentalist, you can understand how it's slightly important and useful in a completely different context of understanding how lines are distributed inside the conductor and how they might behave, how they melt, the shapes that they might take, the different types of lines that might behave like, how they can melt the surface while remaining solid like inside. There are many other questions that are very beautiful that come up here. So this is the first of my 3 talks. This is the most mathematical of all of these talks. I have not done very much mathematics, there's a little bit of equations here and there. The rest of these, the second and the third talk will be very descriptive in character. So this is the one where I thought was really targeted and just doing physics rather than physics. This is just in another area. And so let me just stop there. I'm happy to take questions from you.
If anyone has any questions, if you feel free to ask them.
Yeah.
So you said you were curious if there is a glass space there. What would protect you to think if there is a glass space?
Experiments. And in fact, it turns out that really much of the space diagram is with glass.
So wouldn't we associate some kind of disorder?
Yes. So the disorder comes because this is embedded inside a crystal. I'm taking nanobium, I'm taking hydroxyselenide or something, it's a crystal. But it's a quantum mechanical effect that combines electrons within that crystal into this quantum state that has all these peculiarities. But nevertheless, these lines are sensitive to the microscopic defects inside the crystal. If an atom is missing from a regular position, then there is dislocation or something, we see that. So there is always disorder present inside the crystal that affects the positioning of these lines. It's now understood that it's really a glassy state in addition to the state that I described, triangular or something. And that's really much of the phase diagram. So much of people's interest in this art goes into understanding what is the nature of the glass.
So, I have a question that you were describing how the electrons are paired and therefore they acted as bosons, so they could share the wave function. So, these bosons also have to pass through the conductor.
That's right.
There is an associated, drift velocity. So,
No, that it's not there because they're now in one quantum state. Because they're in one quantum state, they each electron can't do things individually. The whole quantum state does it.
okay, so then there's no definite, velocity argument is not relevant.
The velocity of individual electrons is not relevant here. You have to ask what is the velocity that the entire quantum state is carrying, in which you have 10 to the 23 electrons. And because they're all moving together, they all are condemned to obey the same law that every other electron is doing in this quantum state, that's why you have the macroscopic behavior.
And we wrote that expression of G with respect to the vector potential, the big lambda. What is the big lambda?
That's just a multiplying constant that one can work out what that is. That is if J is proportional to A, but more precisely del cross A is proportional to del cross A, the magnetic field. From which I derive that relationship, the magnetic field dies exponentially. But those constants there are things that involve the number of the superconducting density of electrons, the charge of the electron, the mass of the electron. You can work those things out. They're in the form that I wrote in some other equation over there, what it depends upon.
Vector potential is always proportional to J.
No. In this case, the relationship between J and A is valid only in this conductor.
So, like, how do we know what the boundary is? When do we stop going from sigma A to lambda A?
So that was the question that people struggled with. Everybody knew the sigma equal to n squared tau divided by n formula. But they could not explain superconductivity using that. So that was the 30, 40 years it took for people to understand that unlike J equal to sigma, you need a different relationship in the superconductor. And that relationship weirdly involves the magnetic field. It's del cross J is proportional to the magnetic field. That's not obvious. I mean, it took many years, many brilliant people many years to figure out. But the crucial part of that was the Meissner effect. Figuring out that the superconductor was not just a boring thing, it was definitely doing something to magnetic field inside it. It was trying to push them out.
Why is the lattice a plastic?
Why is that?
So there are two questions here. First of all, there are lines through which the magnetic field.
That's it. The lines of magnetic field.
And between that, there are superconducting regions.
So the line is to be thought of as being normal in the core, and that it becomes more superconducting and move away from it. So if I have two lines far away, the field is large, it's normal here, superconducting here, and then goes back to being normal again.
As temperatures go down, let's say, then the lines come closer or not?
No, it will keep the line spacing dictated only by the magnetic field. At large magnetic field, they're closer together. At low magnetic field, they're far away from each other. What temperature does is to allow them to fluctuate as a dense object. The lower you go, the less they fluctuate. The higher you go, the more they do the rock.
Alright. So they become better. But the lattice.
That's what they tell. So
Okay.
melting is sort of the extreme limit of bringing it up. So the thermal, when you increase the temperature, they begin to shake around.
Does the lattice also disturb?
Yes, so the lattice also, you can see the lattice also moving around in this direction. Until the point where the amount is moving around the cooling box becomes large enough that it's preferable for it to melt. That's really how ordinary solids melt. If you increase the temperature, they're all sitting in the position, solid lattice position. They begin to jiggle around more and more and more and more and more. Until such point that they're jiggling out so much, that it's preferable to form a liquid rather than sphere solid. Same idea is here.
And the lattice is this, that structure because it's just AC, closest packing mechanism.
Exactly. That's only because of closest packing. So you can get somewhat more exotic examples if you have, it's closest packing only for central force interaction.
Yeah.
But if you have more complicated angular current interaction, you have a square lattice, you have other funny lattice. That's also known.
We can talk about the lattice in smaller dimensions. What is this like? Let's say it's a 1D, 2D,
Yeah.
and then the lines go perpendicular. So then it's just.
Then you have superconducting
Yeah.
disks, a little thing rather than lines. So people study that. You can study films of superconductors that are very thin, and you can study bulbs of superconductors that are much thicker. In the bulb case, it's like lines. In the other case, it's like little disks that move around. It's the same idea.
So you talked about like three states: solid, liquid, and gas in that diagram. So does scientists have done these experiment on the fifth state, like Bose-Einstein condensate,
So
for
the-
superconductivity?
So the superconductor is a state
Yeah.
like that, but you don't embed them into these phase diagrams. The completely classical phase diagram of different
No, I'm
states.
talking about the Bose-Einstein condensate, the fifth.
So even the Bose-Einstein condensate, that you can study the phase diagram of the condensate. You can increase the pressure, increase the temperature, say which is the superfluid state, which is the normal state. Are there different types of superfluids which they can be?
And does the superconductivity can be can get in the Bose-Einstein condensate?
So superconductivity is understood like Bose-Einstein condensation, except it's of pairs. That's one useful way of thinking about what is happening. It's not the absolutely right way, but it's certainly a very useful way.
Thank you so much, sir, for this wonderful lecture. At the end of today's session, I would like to thank our principal, our vice principal, our head of the department, staff advisor, and everyone else who helped in making day one a true success. Thank you. So everyone in the audience is requested to kindly gather in the science lawns for a quick photograph and some light refreshment.